Imagine someone hands you a dashboard packed with information about model performance. Accuracy, F1 score, ROC curves, precision recall curves, root mean squared error, mean absolute error, R squared. What's the story here? Is the model good? Or if we're comparing models, which one's the best? It's very rare for a model to beat all other models across all performance metrics, so the answer is usually not obvious. This is where it becomes important to understand the problem, the models, and the evaluation tools well enough to bring them together into a coherent story that leads to a good decision. Now, there are many problems, models, and evaluation metrics out there, so let's start simple and focus on a popular metric for evaluating binary classification models, the ROC curve. And to understand ROC curves, we need to start with something even simpler, recall. Imagine you've built a hot dog or not hot dog image classifier. The classifier looks at a photo and predicts whether it's an image of a hot dog or not. This is known as a binary classification problem because there are two classes of images, the thing we're trying to detect, also called the positive class, and everything else, also called the negative class. As your classifier goes through the dataset, it will label the image hot dog or not hot dog. Sometimes it's going to get it right, and sometimes it'll get it wrong. Recall measures how well the model detects the positive class. For a collection of images, it's the fraction of hot dogs that the model correctly labels as hot dog. So if there are 10 images of hot dogs and only 5 of them were labeled hot dog, then the classifier has a recall of 0.5. But here's where I want to get a little unconventional, because just like we can talk about the model's ability to detect the positive class, we can also talk about its ability to detect the negative class. In other words, we could ask the question, out of all the images that are not hot dogs, what fraction did the model correctly label as not hot dog? In this case, there are 10 non-hot dog images and 7 were labeled correctly, meaning the recall for the negative class is 0.7. So conceptually, we can think of it as having two recalls. The recall for the positive class, the probability that the classifier correctly labels a hot dog image as hot dog, and the recall for the negative class, the probability that the classifier correctly labels a non-hot dog image as not hot dog. And in a perfect world, we'd have high recall for both classes, because that would mean the model is correctly labeling most of the hot dog images and correctly labeling most of the non-hot dog images. In practice, though, there's almost always a trade-off. For example, imagine you have a score-based binary classifier that outputs a score for each image. To make its final prediction, the model compares that score to a threshold. If the score is above the threshold, the model labels the image hot dog. If it's below the threshold, it labels it not hot dog. Here, the threshold effectively controls how selective the model is. A high threshold makes the model very selective. Many images will fall below the threshold, so many images will be labeled not hot dog. This means the recall for the positive class will be low because many of the hot dogs will be incorrectly labeled. But at the same time, the recall for the negative class will be high because many of the non-hot dog images will be correctly labeled. A low threshold does the opposite. The model becomes less selective, labeling more images as hot dog, which tends to increase the recall for the positive class, but will decrease recall for the negative class. This push and pull between the two recalls isn't unique to score-based models. Any mechanism that makes the model more or less selective will tend to produce a similar trade-off. How this trade-off plays out across all levels of selectivity is exactly what the ROC curve, or Receiver Operating Characteristic Curve, is designed to visualize. On a ROC curve, the y-axis shows recall for the positive class, also called the true positive rate or TPR, and the x-axis shows 1 minus recall for the negative class, also called the false positive rate or FPR. For any given binary classification model, each level of selectivity produces a single point on this coordinate plane. A point in the bottom left corner might appear when we have a model that is extremely selective about what it labels as positive, meaning it labels almost nothing as hot dog. Recall for positives would be low, but recall for negatives would be high. A point in the top left corner is the ideal scenario because it means that for some level of selectivity, the model's recall for positives is high and its recall for negatives is also high. Such a model correctly labels many images, hot dog and not hot dog alike, so near perfect classification. A point in the top right corner might occur at very low selectivity levels, where the model thinks almost every image is a hot dog. Recall for positives would be high, most hot dog images would be correctly labeled, but recall for negatives would be low, meaning many non-hot dog images are mislabeled hot dog. This region represents more aggressive classifiers that aren't afraid to cry hot dog and be mistaken. Lastly, a point in the bottom right corner means recall for positives is low, most hot dog images are labeled not hot dog, and recall for negatives is also low. Most non-hot dog images are labeled hot dog. This seems like a terrible model because it's getting most of the labels wrong for both classes. In reality, this has a very easy fix. If you just flip the model's output labels, both recalls will automatically jump to the top left corner, which is great. Outcomes in this region typically occur when we've gotten our labels flipped somewhere along the way, so just watch out for that. Now, for any given model, if we fix the level of selectivity, we'll get a point in this coordinate plane. And as we vary the model's level of selectivity, we'll get several points on the coordinate plane. Here, different levels of selectivity often result in the same x value, FPR, but different y value, TPR. Now, most popular software typically condenses these multiple y values into one, for instance by taking the maximum y, so that each x value corresponds to a single y value, and this resulting step function is the ROC curve. Moving along the ROC curve from left to right shows the price we pay in terms of FPR to achieve a certain TPR. Now, suppose we've developed a model and we're currently operating at a selectivity level that gives us a recall of 0.9 for the positive class. On paper, that sounds great. 90% of positives are being detected. But when we look at the ROC curve more closely, we notice something interesting. If we step to the left along the curve to a positive recall of 0.88, the negative recall increases by 0.1. So now we have a real question to ask ourselves. Is that extra 0.02 in positive recall worth the 0.1 decrease in negative recall? The ROC curve doesn't answer that question for us, but it makes the trade-off visible. It tells us what we gain and what we give up. In some applications, a high positive rate might be critical, and in others, reducing false positives may matter more. The curve just lets us see those options clearly. For threshold-based classifiers where the model assigns a score and labels an instance as positive if the score exceeds a threshold, the ROC curve is monotonically increasing as the threshold decreases. A knee in the curve can be especially informative here because once you know which threshold corresponds to the knee, lowering the threshold any further will increase the false positive rate faster than the true positive rate, which may not be worth it. Now, I can't stress enough that whether a trade-off is worth it is highly problem-dependent, but even so, the knee of the ROC curve can serve as a useful point of reference. Another possible use case for ROC curves is when comparing models. Suppose we have a really naive classifier. It just looks at an image and randomly decides hot dog with probability p and not hot dog with probability 1 minus p. We already know this isn't going to be a good classifier because it's not actually learning anything from the data, but that doesn't mean it won't sometimes get it right. For example, if p equals 0.9, then each time the model sees an image, it labels it hot dog with 90% probability, regardless of whether the image is actually of a hot dog or not. And because the labels are generated as independent Bernoulli trials, about 90% of all images will be labeled hot dog. This means roughly 90% of the actual hot dog images will be labeled correctly, giving a positive class recall of 0.9. At the same time, about 90% of the non-hot dog images will be labeled hot dog, so the recall for the negative class will only be 0.1. Generally, for any probability p, this naive classifier will have an expected positive recall of p and an expected negative recall of 1 minus p. So if you plot the expected ROC curve, it will look like the line y equals x. Now, suppose we build another model, hopefully a better one. If the ROC curve of this new model ever dips below the diagonal, that tells us something important. For the same false positive rate, the model is catching fewer true positives than random guessing would. In other words, the trade-off is worse. We're paying the same price, but getting less value. If this happens in just a small region, it highlights that the model struggles there, but if the entire curve sits below the diagonal, that's usually a red flag. Often, it means the positive and negative labels were flipped. In fact, flipping the model's predictions rotates the ROC curve 180 degrees about the point 0.5, 0.5, turning a worse than random classifier into a better than random one. So, a curve entirely below the diagonal usually points to a labeling or setup issue, not that the model itself is useless. In general, if you're comparing two models and one model's ROC curve sits entirely above the others, we say it dominates the other. For every false positive rate, the dominating model achieves a higher true positive rate, so on the dataset we're evaluating, it's objectively better at balancing the trade-off between positive and negative recall. So, assuming the FPR versus TPR trade-off is what matters for our use case and that our evaluation dataset reflects the real application, domination gives us a clear data-driven way to compare models. Sometimes, however, one ROC curve does not strictly dominate the other. The ROC curves may cross. One model might perform better at very low false positive rates, while the other performs better when we tolerate more false positives. A natural way to summarize and compare overall model performance in this case is to look at the area under the ROC curve, or AUC. In a sense, the area under the curve captures which curve is higher on average, and for threshold-based classifiers with continuous scores, it has a particularly clean interpretation. It's the probability that the classifier assigns a higher score to a randomly chosen positive instance than to a randomly chosen negative instance. To see why this is true, let's start by writing the ROC curve as a function y equals f of x, where y is the true positive rate and x is the false positive rate. Then the area under the curve is nothing but the integral from 0 to 1 of f of x. Now, because we're talking about threshold-based classifiers here, we know there exists a function g of t such that x equals g of t, where x is the false positive rate corresponding to threshold t. Using a change of variables, we can rewrite the area under the curve integral in terms of the threshold. After the change of variables, f of g of t is just the positive recall at threshold t, which is the same thing as the probability that a randomly chosen positive instance has a score greater than or equal to t. Similarly, g of t is 1 minus the negative recall at threshold t, which is the same thing as the probability that a randomly chosen negative instance has a score greater than or equal to t. Substituting these into the integral, we have this, and at this point it helps to think about the integrand in two pieces. Focusing on the first piece, notice that we can trivially condition on s minus equals t without changing anything, and this term is equal to the probability that s plus is greater than or equal to s minus, given that s minus equals t. Now, turning our attention to the second piece, notice that the probability that s minus is greater or equal to t is the same thing as 1 minus the probability that s minus is less than t. And if we make this substitution in our derivative, we end up with this. The negative sign cancels the one outside the integral, leaving this, and this term is the probability density function of s minus evaluated at t. Now, rewriting the integral in this way helps us recognize that this is nothing but the probability that s plus is greater or equal to s minus expressed using the law of total probability, which proves that the area under the curve is exactly the probability that a randomly chosen positive instance has a higher score than a randomly chosen negative instance. A higher area under the curve generally means the model does a better job separating positives from negatives when assigning scores and is therefore more likely to perform well in practice. So we've gone through what a ROC curve is, how it shows trade-offs, and how it can help us compare models. One thing to keep in mind is that interpreting ROC curves can be tricky when your dataset is highly imbalanced. For example, imagine a dataset with 10 positive instances and 1 million negative instances. Now, suppose we're working with a threshold-based classifier where increasing the threshold from T1 to T2 raises the true positive rate by 0.3, while the false positive rate only increases by 0.01. On the plot, switching from T1 to T2 looks like a no-brainer. We get a huge gain in TPR for only a tiny bump in FPR. But if we look at the raw numbers, the picture changes. That 0.01 increase in FPR represents 10,000 extra false positives, while the 0.3 increase in TPR represents just 3 additional true positives. Suddenly, whether moving from T1 to T2 is really worth it becomes less clear. Now, there's nothing wrong with the ROC curve itself. It accurately shows the relationship between TPR and FPR for this dataset. The tricky part comes when we interpret it, because ROC curves don't show raw counts on the axes, so it's easy to fall into the trap of treating the rates as if they're percentages of raw counts on the same scale, which is not even close to true for highly imbalanced datasets. In these cases, other evaluation tools like precision recall curves can give a clearer picture of how well the model is performing, but that's a story for another time.